Hello, we are starting our third installment for NMR. Here we are going to talk about, I have a worked example ready to go. And so what we are going to see here, based off of what we've talked about so far with splitting, and understanding the environment, electronegativity, we are going to look at this worked example. So integrated proton NMR for a compound with the formula C4H10O is shown below. And so what we see in this spectra, we have two different sets of peaks. We also see, based off the formula, we can calculate the degree of unsaturation. And we know that to be 2 times the carbon plus 2 minus the number of hydrogens divided by 2. Now the big thing here is you notice that I have left off nitrogen and halogens because they're not there, and oxygens are always ignored. So when we follow the formula, we see that we get a degree of unsaturation of 0. Now, that tells us that there are no rings and that there isn't a pi bond. All right, so no rings, no pi bonds, two sets of peaks for proton signals. So that tells us a lot right there, right? For in terms of what could we have with oxygens, right? The type of functional groups we're typically going to see are either going to be carbonyls or esters that have a carbonyl, or carboxylic acids that have a carbonyl. Now looking at single bonds, we could have just an alcohol functional group or an ether functional group. Now, with that being said, we know that anything that has a carbonyl is excluded as a possibility based off the DOU, because a pi bond would give us a degree of unsaturation of 1, and we see it 0. So then really we're looking at single bond options, which would be our alcohol or our ether category. Now, we haven't talked about it yet, but I can tell you based off the peaks that I see, the OH, having an OH is not going to happen, because that the hydrogen that's on this oxygen would give us a very broad singlet peak, and we do not see that. In particular, we at least know the difference between a singlet, a triplet, or a quartet, so you can tell we don't have those. We have a triplet and a quartet. So alcohol's out, so we're really looking at an ether where we have COC, right? All these single bonds. And the fact that we have two sets of signals for 10 hydrogens means that we have some symmetry. We have to have symmetry in our structure. And so I first speculated that therefore the ether probably is going to have 2 carbons on one side and 2 carbons on the other. Right? 2 carbons, right? Each one of those carbons would give us different hydrogens. And if they are the same, say ethyl and an ethyl, right, we would see that the first 2 carbons attached to the oxygen are the same, and then the farthest carbons apart are going to give us the same hydrogen signals. So, if looking at that in the realm of, okay, well, then that means we're looking at diethyl ether, possibly. So CH3, CH2, O, CH2, CH3. Based off symmetry, we know that these hydrogens are the same at the ends, and then these 2 middle hydrogen sets of hydrogens are going to be the same. So really, the analysis that I'm going to do, or the predictions that I'm going to do right now, are really only going to look at one side, because we know that these A hydrogens are the same, and we know that these B hydrogens are the same. So looking at our A hydrogens, we have 3 hydrogens here, and we want to figure out, well, what type of splitting would they give us based off the number of neighbors. So remember, when we look at our neighbors, the hydrogens are going to go to the next house and see who lives there. So the next house has 2 neighbors that live in it. So the signal for these hydrogens would be n plus 1, or would be 2 plus 1. So we should see a triplet for these hydrogens. Then looking at these two hydrogens would give us the same signal. They are chemically equivalent, and they're also equivalent to these 2 as well. So we're going to see these 2 have 3 neighbors, so they should give us 3 plus 1, or a quartet. Now, does it make so based off the only splitting that we're going to see, a triplet and a quartet looks good. One other thing we could check would be also looking at where they are in the realm of upfield versus downfield. So when we look at the hydrogens that are closest to the electronegative oxygen, these hydrogens are the closest. So we would expect them to be the most downfield. And remember, these hydrogens, the B hydrogens, gave us a quartet. Our quartet is more downfield than our triplet. So everything seems to be pointing at my structure is diethyl ether. Okay, and just to see the answer, it was diethyl ether. Of course, I did have the added benefit of I knew these slides backwards and forwards, but don't try to judge me right now. All right, next up, looking at proton equivalency, looking at some strangeness that could be a concern for you. For proton equivalency, we need to talk about a couple of scenarios or vocabulary terms. Specifically, I want to talk about what's called enantiotopic hydrogens and diastereotopic hydrogens. So if we look at a structure, you notice here we have butane. So based off of symmetry 1 and 4, those positions are symmetrically the same, and then looking at 2 and 3, these two positions are symmetrically the same. Granted, it is a 4-membered chain. Single bonds have free rotation about them. Now, in terms of looking at the hydrogens on either carbon number 2 or carbon number 3, you see that these are called what's called pro-S or pro-R. I don't really care if you know what that means. But if we look at, say, doing a mock reaction or a fake reaction, and we replaced one of these hydrogens with X, right? In this case, let's say we're doing radical bromination, right? We understand that radical bromination would substitute a hydrogen that's the most substituted. So in this case, these two secondaries would be one of our options. So if we replaced one of the hydrogens with a bromine, we know that we have then created a new chiral center. And of course, with that being said, the bromine could add from the top or from the bottom, so we have a racemic mixture of products, right? We have the R and the S forms. Now, when we look at this product, we went from no chiral center to having the creation of a new chiral center. So we would consider those hydrogens that we replaced, right, with the X, those would be enantiotopic hydrogens. Okay, in replacing them, we created a pair of enantiomers. All right. Next up, we have diastereotopic. So remembering what a diastereomer is, right, you have two chiral centers and only one of them changes, right? So let's go back. Now we've changed. We're no longer looking at butane. We have but 2 enol. All right, so we have an alcohol at the carbon 2 position. And so when we look at the carbon 3 position with these two hydrogens, we now see that if we were to swap those with X, whether it's a chlorine, a bromine, whatever, we see that we have created a new chiral center, right, where the first chiral center, right, the one at C2, didn't change, right, wedge, wedge, wedge. So that tells us that the first chiral center at C2 didn't change, but we have the possibility of getting two different absolute configurations at C3. So we've created a pair of diastereomers. So with that, we would consider these two hydrogens to be diastereotopic hydrogens. Right? So good vocabulary to know. Enantiotopic and diastereotopic. Okay, now why do we care about these vocabulary terms? Specifically, why do we care about our diastereotopic hydrogens? Well, they can actually give us different signals. So specifically, when we look at this structure right here, I'm going to go ahead and redraw it for clarity because I have kind of butchered the structure a little bit inadvertently. All right, so going back and remembering, we have, in this scenario, the two hydrogens here are diastereotopic. This is a chiral center, and so when we look, the hydrogens here, if we replace them, we would get a pair of diastereomers when we replace them. So if we were to look at these two hydrogens, they would actually give us two well-resolved separate signals. And so what we see here are, in essence, each hydrogen gives me a doublet of doublets. So, and if you notice, it's 1, 2, 3, 4 peaks, and each one of those hydrogens gives me 4 peaks, and they are well resolved. They don't bleed together. I can see them distinctively different from one another. Now, why does this happen? We can go back to looking at it how we would a Newman projection. So in particular, remember this wedge? I'm going to say that means that the OH at that carbon, at the dot carbon, is on the right. So on the circle carbon, the wedge hydrogen's on the right. So you see, I'm ignoring all of this carboxylic acid looking stuff, right? I'm just putting the hydrogens and the OH, all right? And so therefore, when I talk about this dash, right, this one right here, versus the hydrogen that we know to be a dash here, all right, we can see that type of Newman projection interaction. And specifically, if you notice, the two wedged species, the OH and the hydrogen, those are gauche to one another, while the two dashed hydrogens, those are gauche to one another. So we know that these gauche interactions and Newman projections do have energy associated with them. So that's why we can kind of see how these two gauche interactions are well resolved, because they have a distinctive difference in their energy level. All right, and so or in their stability, or aka energy. All right, and so the big thing here is we see, if we were to consider these two hydrogens to be equivalent, right, they only have one hydrogen neighbor, so they would give us just a doublet. But we don't see just a doublet anywhere. We see a doublet of doublets, a doublet of doublets, a triplet, and a broad singlet. And that broad singlet is kind of the example of that OH that we saw when I talked about the previous worked example that we did at the beginning of this video. I told you how we would see that as being a broad singlet if it was an OH, and so that's kind of what we're looking at there with that broad singlet. I have actually kind of put dashes in there to show the area under the curve, to show how much broad it is, how it is more broad than the other peaks. All right, but anyway, so big thing here, why do we care about diastereotopic hydrogens? They can give us this weird separation of signals to where these two are no longer considered chemically equivalent, and we get this weird doublet of doublets stuff. All right, so that's something that can happen. Another thing that can happen, I've lumped it in with kind of diastereotopic hydrogens, but when we look at pi bonds, previously, the first video, I can't remember, but the first or the second video, we talked about 2-chloropropene, that structure right there, and we talked about how the two hydrogens on this carbon were distinctly different. All right, and that's going back to looking at kind of that Newman projection where you would have the top hydrogen here is eclipsed with the chlorine, the bottom hydrogen here would be eclipsed with the methyl group, right? So if we look at this structure, I've already kind of edited it severely enough that I think I need to redraw it. But so when we look at this structure right here for the NMR spectra shown, you'll see here these two hydrogens, as we saw in the case over here, these two hydrogens are going to be different, because now you have this hydrogen is eclipsing with that one, and this hydrogen is eclipsing with a methyl group. So what we're going to see is these two hydrogens are no longer chemically equivalent, so they'll give us separated signals. Now, in particular, for this hydrogen, right, how many neighbors does it have? Well, go to the next house, and it only has one neighbor. So it does have an n equal to 1, just as this one has an n equal to 1. Right? So what we're going to see is this hydrogen gives me a doublet, right? N plus 1 is 2. So doublet and a doublet. And so that's what we see right here with this doublet of doublets. Or sorry, it's a doublet of doublets, or it's that would be a doublet of singlets, All right, but whatever. So we have this doublet of doublets here based off the fact that these two hydrogens are resolved in energy enough from one another, right? Eclipsing CH3 versus eclipsing hydrogens, that's a huge amount of energy. That's not as much, right? So That's why we see this weird looking multiplet here. And so one of the things that I pointed out in a previous video, right, whenever we see a multiplet, think about weird things happening. So with multiplets, you're going to see a label of a multiplet somewhere whenever you have pi bonds. All right, so I called that a multiplet or a doublet of doublets. But then also this crazy multiplet here for that hydrogen, because it has 3, 4, 5 neighbors, so you might think a sextet would occur. But that hydrogen does not give you a sextet, it gives you something weird. There's technically, if you look at each individual peak, it's 1, 2, 3, 4, 5, 6, 7, 8. You have 8 peaks, and that's because this hydrogen sees that one differently than it sees this one. And then that hydrogen also sees the CH3 differently. Because of this pi bond, it's locked in place, so it sees the three different sets of hydrogens all differently, so you're having all 3 signals kind of clustered in the same frequency range, and they don't overlap perfectly. They're skewed from one another, and so they look weird, so they give you the multiplet. So pi bonds can give you weird multiplets, as well as diastereotopic hydrogens, right? Those can give you these weird doublet of doublets. Okay, and so also anytime you see a structure that is locked in place, you can see these multiplets taking place. Okay, so like anytime you have a ring, right? So when you have a ring, let's say you have cyclohexane, right? You know that you have an axial and an equatorial hydrogen, so sometimes that can give you weird multiplets as well. Okay, so do be aware of that. Okay. Now, looking at, in particular, looking at benzene, right? You can have disubstituted benzene, right? So it has two groups on it, right? But you have a 1,4 substitution, a 1,3 substitution, but you can also have a 1,2 substitution. And so in particular, I'm looking at a benzene ring that has OH and CH3 bound to it, whether it's a 1,4, 1,3, or 1,2. And the interesting thing here is when we look at the hydrogens bound to the aromatic ring, bound to the benzene ring, it can tell us a lot about how those two groups are structured and how those two groups are attached to the ring. So when we look here, this CH3 will always give you a singlet, right? That's your CH3 that gives you the singlet right there around 2.2. Your OH is always going to give you this broad singlet, okay? Now, however, when we look at the hydrogens that come off the ring, based off of plane of symmetry, in particular, this structure, the 1,4 substituted benzene, only has one plane of symmetry going here, right? Cutting through the oxygen-carbon bond and the carbon-carbon bond here, right? And so what that tells us is these top 2 hydrogens are equivalent, and then these top 2 hydrogens are equivalent. So really we're going to see only 2 signals in that aromatic frequency, right? So in the 6.5 to 8.5, we only see 2 aromatic hydrogen signals. And in particular, you notice both of them are doublets, which makes sense because what do we see? This hydrogen has how many neighboring hydrogens? Only 1. This hydrogen has how many neighboring hydrogens? Only 1. So 1 plus 1 is 2. 1 plus 1 is 2, right? So doublet, 2 doublets. Okay. Now, if we change it instead of a 1,4 to a 1,3, we now see that there is no plane of symmetry in this structure. And so we're actually going to see 1, 2, 3, 4 different sets of peaks in our aromatic frequency range for NMR. And so when we look here, you actually only see 3 because some of these do bleed together. If you look here, 6.85 versus 6.7 versus 6.6, all of those are very close to one another, so they do kind of look like they start to bleed together. And in particular, what you should be seeing here, you have, if you were to look at each one of these hydrogens, as I've done over here, right, the hydrogen right here between the OH and the CH3, it has no neighbor, so it gives you a singlet. Coming over here to this 6.6 one, it has one neighbor, so it gives you a doublet. The next one over has 2 neighbors, gives you a triplet. and then this hydrogen here gives you a doublet because it only has one neighbor. So in particular, what we would see if they were highly resolved, which they're not, unfortunately, but that would be something that I would actually point out to you if you needed to see it. Like if you were given that spectra, I would say this is actually a singlet, two doublets, and a triplet, so that you know that it's 4 different signals, and it tells you, it gives you an idea of what the structure is. But what we see here is 4 different signals, a singlet, 2 doublets, and a triplet. Now, the last scenario we have for disubstituted benzene, if it's a 1,2, right, you're going to see in this 1,2 disubstituted structure, there's no plane of symmetry yet again, so you have 1, 2, 3, 4 different hydrogens. And when you look at the neighbors that they have, right, this hydrogen only has 1, so it gives you a doublet. These 2 hydrogens each have 2 neighbors, so they both give you triplets. And then this hydrogen here, which doesn't look like a hydrogen based off of my H, but this hydrogen here only has 1 neighbor and gives you a doublet. So you see here the 4 different peaks are 2 doublets and 2 triplets. So you can see here both the 1,3 and the 1,2 gives you 4 signals, but the 1,3 has a singlet, the 1,2 does not. So you can tell there is a big difference in terms of what we're going to see. If it's not the number of signals, it's how the signals appear as singlet, doublets, or triplets. All right. So that's something very important for you to be able to do. Right. Look at a proton NMR. Tell me what the splitting would be, how many different signals you have. Okay. All right, and so just looking at some more practice really quickly, when we have a pi bond, right? So when we look at the structure we have here, there's a pi bond between C2 and C3. So whenever we see that, we know that this hydrogen is going to give us something wonky, and then this hydrogen is going to give us something wonky, because each one of them is bound to a sp2 hybridized carbon. And so when we look, right, this hydrogen has 1, 2 neighbors. So you might think, oh, okay, so the splitting I'm going to see is going to be n equals 2, so 2 plus 1 is 3. However, when we go and look, you don't see 3 peaks, you see 4. And that's because, yet again, this pi bond makes it to where the hydrogen sees this neighbor and this neighbor differently. So you're going to say, okay, so it had a neighbor over here, so that's 1 neighbor, you see a doublet. Here's another neighbor that I see at a different time, so it's a doublet. So I get a doublet and a doublet. So that's why you see here 2 peaks of equivalent height, that's 1 doublet, and then 2 peaks of equivalent height, there's the second doublet. So you have a doublet of doublets. Okay, all because of that pi bond. All right. And the other thing I kind of want to point out here is, since this hydrogen it only has 1 neighbor with hydrogens, you do just see a doublet, right? So the green, so here it's elaborated. I know it looks like they're very far apart, but this is a doublet, okay? That green peak right there, which is so smushed together, this is a doublet, all right? It's not a doublet of singlets, it's a doublet. But I did want to point out this aldehyde hydrogen. All right, when you look at its neighbors, right, it lives in that carbon house, and so it has 1 neighbor. So you would expect a doublet, and when you look at it kind of elaborated here, zoomed in, you do see a doublet. Okay, and remember, aldehyde hydrogens, they're usually between the 9 to 10 ppm range, and your carboxylic acid hydrogens, those are between the 10 to 13 range. All right. Okay, and then we can look at one other example real quick, looking at this 3-bromo 1-phenylpropene. And in particular, I want to pay attention to this hydrogen here, the C2 hydrogen. So when we look at the spectra we could get, okay, when you look at, when you just look at the structure here, you see that, okay, there are 2 hydrogens there. So it has 2 neighbors on this side, 1 neighbor on that side. So you might think that n is equal to 3, so you should see n plus 1 equaling 4. So you should see a quartet. However, when we look at that signal, there are actually 1, 2, 3, 4, 5. There are 5 peaks, not 4. And so that is because, yet again, remember, when you have this pi bond here, it will see these 2 at a separate instance than when it sees this one. All right. Technically, I'm probably giving you the wrong terminology here, but I'm trying to help you. It sees this one, these neighbors separately than when it sees that one. Okay, so And so what happens here is you think about, okay, so it has two neighbors here. So then so n is equal to 2. So on this side, n is equal to 2. So you get 2 plus 1 equals to 3. So at that instance, it gives you a triplet. Then you look over here and it says, okay, so over here it's n is equal to 1. So n plus 1 is equal to 2. So that instance, it gives you a doublet. So what you're actually going to see are 5 peaks here. And important to mention here, it's 5 peaks, but it's not going to be a quintet. All right. Remember, like anytime you talk about doublet, triplet, quartet, there's symmetry involved, right? The middle peak for a quintet is the tallest. Then you take one step to the left, one step to the right. All right. Those are the next two tallest, and then you take a step to the left, a step to the right. Those are the smallest two, right? So there's symmetry there. But when we look at the 5 peaks we get there is no symmetry. It is, and so here it is. It's a little bit easier to see, right? It goes up, down, right? So you do see that it's not there, okay? Just making sure we do see that. All right. Okay. All right. So with that, I'm going to stop here, and we will finish up in our last video. So video number 4.